Dear student, welcome in the class of mathematics. Students, in regular classes, we have already studied linear differential equation with constant coefficients. In this lecture, we have to see some theoretical questions which are very important. So let us recall definition of linear differential equation with constant coefficients, that is LDE. The differential equation of the type d raised to n plus p1 d raised to n minus 1 plus p2 d raised to n minus 2 plus dash 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 pn into y is equal to capital X, where p1, p2, p3, pn are the constants and capital X is function of small x and capital D is equal to d by dx is called linear differential equation with constant coefficients. Shortly, we say it is LDE. Here, d raised to n plus p1 d raised to n minus 1 plus p2 d raised to n minus 2 plus dash 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 pn. This is the polynomial in capital D. We can shortly say this is function of capital D. So we can write this differential equation as f of d into y is equal to capital X. The general solution of this linear differential equation is given by y is equal to complementary function plus pi. Here pi means particular integral and which is given by pi is equal to 1 upon f of d into capital X. We have seen this result. Now see the important question. Show that 1 upon d minus m into capital X is equal to e raised to mx integration e raised to minus mx into capital X dx. Here capital X is function of small x. We have to show value of this is this. So solution. Let write f of d is equal to d minus m. We know linear differential equation is f of d into y is equal to capital X. Put f of d as d minus m, so we get d minus m into y is equal to x. Take this y inside one, so dy minus a my equal to capital X. As d is equal to d by dx, so we get dy by dx minus m into y equal to capital X. We observe that this is the differential equation dy by dx plus py equal to q. That is the linear differential equation. Here p means minus of m and q means capital X. Both are functions of x. Here m is a constant, so we can treat it as function of x. So capital P as well as capital Q both are functions of x. So this is the linear differential equation. So we can solve this by using its general solution is given by y e raised to integration p dx is equal to integration q into e raised to integration p dx plus c. Now put here values of p and q, and so we get y e raised to integration value of p which is minus m into dx equal to integration value of q which is x e raised to integration minus m in dx plus c. Here m is constant, so take this minus m outside of that integral, and so we get y e raised to minus m integration dx equal to integration x minus m outside e raised to minus m integration dx plus c. Integration of dx is x, and so we get y e raised to minus m into x equal to integration x e raised to m into x dx plus c. Transfer this e raised to minus mx to that side. So its power will become positive, and so we get y equal to e raised to mx into integration e raised to minus mx into capital X dx plus c into e raised to mx. We can write this y is equal to c into e raised to mx plus e raised to m into x into integration e raised to minus mx into capital X dx. As we know, general solution of the differential equation is y is equal to cf plus pi. C into e raised to mx, here m is the factor of d minus m, factor of f of d, and so this represents the complementary function. As the first term is a complementary function, means second term should be particular integral, And so we get pi is equal to e raised to mx into integration e raised to minus mx into capital X dx. But we know pi means it is 1 upon f of d into capital X. So put value of pi as 1 upon f of d into x here equal to e raised to mx into integration e raised to minus mx into capital X dx. But what is f of d? F of d is the d minus m. So put value of f of d here, and so we get 1 upon d minus m into capital X is equal to e raised to mx into integration e raised to minus m into x into capital X dx. And hence proved. That was we have to show. And so we get the result 1 upon d minus m into capital X is equal to e raised to mx into integration e raised to minus mx into capital X dx. Now we have to see next question. If capital D is equal to d by dx and f of d is a polynomial in capital D with constant coefficients, then show that 1 upon f of d into e raised to x is equal to e raised to x upon f of a, where f of a not equal to 0. Here he has given d is d by dx, f of d is polynomial in D with constant coefficient. Using this, we have to show 1 upon f of d e raised to x is equal to e raised to x upon f of a. Means here we have to put d is equal to a. And given that f of a is not 0. So proof. D into e raised to x is equal to d means d by dx, so d by dx e raised to x. So take derivative of e raised to x with respect to x, which is e raised to x into derivative of x, which is a. So this derivative is a into e raised to x, and therefore we get d e raised to x is equal to a e raised to x. Denote this is equation number 1. Again operate d on both sides, so we get d of d e raised to x is equal to d of a e raised to x. Take this d inside 1, and so we get d square e raised to x is equal to value of capital D as d by dx. So d by dx of a e raised to x, here a is constant, so take outside of that derivative, and so we get this is equal to a outside d by dx of e raised to x. Derivative of e raised to x is e raised to x into a, and so this will become a into a e raised to x, and so we get d square e raised to x is equal to a square e raised to x. Denote this as equation number 2. Now observe equation number 1, equation number 2. D raised to 1 e raised to x is equal to a raised to 1 e raised to x. D raised to 2 e raised to x is equal to a square e raised to x. So continue like this. In this way, we get d raised to r e raised to x is equal to a raised to r e raised to x. Denote this is equation number 3. Now as in question given, f of d is polynomial in D with constant coefficient. So f of d is equal to d raised to n p1 d raised to n minus 1 plus p2 d raised to n minus 2 plus dash 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 pn. Say this is the equation number 4. Now f of d into e raised to x, put the value of f of d, which is d raised to n p1 d raised to n minus 1 plus p2 d raised to n minus 2 plus dash 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 pn e raised to x. Now take this e raised to x inside 1, and so this is equal to d raised to n e raised to x plus p1 d raised to n minus 1 e raised to x plus p2 d raised to n minus 2 e raised to x. Continue in this way. In last term, pn e raised to x. Now observe equation number 3. By equation number 3, d raised to r e raised to x is equal to a raised to r e raised to x. Now see this one, instead of r, here is n. So value of this is a raised to n e raised to x. D raised to n minus 1 e raised to x. Value of this is a raised to n minus 1 e raised to x. And continuing in this way, so we get this is equal to a raised to n e raised to x. Here p1 as it is. Value of this is a raised to n minus 1 e raised to x. p2 as it is. Value of a d raised to n minus 2 e raised to x is a raised to n minus 2 e raised to x plus dash 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 pn e raised to x. Now observe that each and every term contains a raised to x. So take e raised to x as a common, and so this is equal to a raised to n plus p1 a raised to n minus 1 plus p2 a raised to n minus 2 plus dash 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 pn, and that e raised to x outside. Now observe this round bracket. This is of the type d raised to n p1 d raised to n minus 1 plus p2 d raised to n minus 2 plus dash 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 pn. Instead of d, here is a. As this is f of d, so this is f of a. And so we get f of d e raised to x is equal to f of a into e raised to x. Now transfer this f of d to this side, and so we get e raised to x is equal to 1 upon f of d, f of a e raised to x. Here operator 1 upon f of d means it is integration. And here a is constant, so f of a is also constant. So take out this constant f of a outside of that integral, and so we get e raised to x is equal to f of a 1 upon f of d e raised to x. Here you know f of a is not 0. So transfer this f of a to this side, and so we get e raised to x upon f of a is equal to 1 upon f of d e raised to x. Now interchange right hand and left hand side, so we get 1 upon f of d e raised to x is equal to e raised to x upon f of a. Hence proved. That was to show. And so we get the result 1 upon f of d e raised to x is equal to e raised to x upon f of a. Instead of d, we have to put a. But condition is that f of a should be not 0. Hence the proof of the question. Now see the next question. Show that 1 upon d minus a bracket raised to r e raised to x is equal to x raised to r e raised to x upon r factorial. Solution. Consider 1 upon d minus a raised to r e raised to x. We can write this d minus a bracket raised to r as d minus a bracket raised to r minus 1 into d minus a. So this is equal to 1 upon d minus a bracket raised to r minus 1 as it is, 1 upon d minus a e raised to x. So first we have to operate 1 upon d minus a on e raised to ax. As we know, 1 upon d minus m into capital X is equal to e raised to mx into e raised to minus mx into capital X dx. We already studied this result. So instead of m, here is a. So value of this is e raised to ax into integration e raised to minus ax into capital X dx. That is this one. So this is equal to e raised to x integration e raised to minus ax into e raised to ax dx. Here base is same, so take the addition of powers, and so this is equal to e raised to minus ax plus ax dx. So this will become e raised to 0, that is 1, and so we get this is equal to 1 upon d minus a bracket raised to r minus 1 into the bracket e raised to x integration of 1 dx. Integration of 1, which is x. So this is equal to 1 upon d minus a bracket raised to r minus 1 into the bracket e raised to x into x. And therefore 1 upon d minus a raised to r e raised to x is equal to 1 upon d minus a bracket raised to r minus 1 x into e raised to ax. Now we can write this 1 upon d minus a bracket raised to r minus 1 as d minus a bracket raised to r minus 2 into d minus a bracket raised to 1, and this x e raised to x as it is. So this is equal to 1 upon d minus a bracket raised to r minus 2 as it is. First operate 1 upon d minus a over x into e raised to ax. You same this formula, 1 upon d minus m into capital X is equal to e raised to mx into e raised to minus of mx into capital X dx. Instead of capital X, here is x into e raised to x, so here we get x into e raised to x, and instead of m, here is a, and so here we get e raised to x integration e raised to minus x into e raised to x dx. So this is equal to this e raised to x as it is, this x also as it is. Take the product of e raised to minus ax into e raised to ax, base is same, and so we get e raised to minus ax plus ax into small x into dx. So this will become e raised to 0, that is 1. So this is 1 into x means integration x dx only. Now find out integration of x, which is x square upon 2. So this is equal to 1 upon d minus a bracket raised to r minus 2 into e raised to x square upon 2. So this is equal to 1 upon d minus a bracket raised to r minus 2 x square e raised to x upon 2. As see this one, you can write this equation as 1 upon d minus a bracket raised to r e raised to x is equal to 1 upon d minus a bracket raised to r minus 1. You can write this x as x raised to 1 e raised to x upon 1 means 1 factorial. So you can express this equation like this. This is equation number 1. Similarly, we get this equation as 1 upon d minus a bracket raised to r e raised to x is equal to 1 upon d minus a bracket raised to r minus 2 into the bracket x square e raised to x upon, you can write this 2 as a 2 factorial. This is equation number 2. Now observe equation number 1, equation number 2. And so we get 1 upon d minus a bracket raised to r e raised to x is equal to 1 upon d minus a raised to r minus 3 x cube e raised to x upon 3 factorial, and continue in this way. So we get 1 upon d minus a raised to r e raised to x is equal to 1 upon d minus a r minus r. Take here r. If we take here r, here we get x raised to r e raised to x upon r factorial. But r minus r, it is 0. Any number raised to 0 is 1. So this will become 1 upon 1, that is 1. So in this side, we get only x raised to r e raised to x upon r factorial. And this is as it is. And so lastly, we get 1 upon d minus a bracket raised to r into e raised to x is equal to x raised to r e raised to x upon r factorial. Hence proved. That was to show. And so lastly, we get the very important result. 1 upon d minus a bracket raised to r into e raised to x is equal to x raised to r e raised to x upon r factorial. Now see the next example, next question. Show that 1 upon f of d e raised to x is equal to x raised to r e raised to x upon pi of a r factorial if f of d is equal to d minus a bracket raised to r pi of d and pi of a not equal to 0. Solution. Consider 1 upon f of d into e raised to x. He has given value of f of d as d minus a bracket raised to r into pi of d. So put this value here. So this is equal to 1 upon d minus a bracket raised to r pi of d e raised to x. So this is equal to 1 upon d minus a bracket raised to r. Take this 1 upon pi of d outside, 1 upon pi of d e raised to x. You know here pi of a is not 0. And so here you can use 1 upon f of d e raised to x is equal to e raised to x upon f of a if f of a not 0. If f of a is not 0, then we put d is equal to a. Similarly here pi of a is not 0, so put here d is equal to a, and so we get this is equal to 1 upon d minus a bracket raised to r as it is e raised to x upon phi of a. Take this pi of a, 1 upon phi of a outside, so 1 upon pi of a 1 upon d minus a bracket raised to r e raised to x. Now you know by previous result 1 upon d minus a bracket raised to r e raised to x is equal to x raised to r e raised to x upon r factorial. So put this value here, and so 1 upon phi of a x raised to r e raised to x upon r factorial. And therefore 1 upon f of d e raised to x is equal to x raised to r e raised to x upon phi of a into r factorial. Hence proved. And so we get the result 1 upon f of d e raised to x is equal to x raised to r e raised to x upon phi of a into r factorial. If we put here d is equal to a, f of a becomes 0. In last question, f of a was not 0. If here f of a is 0, then we have to use this concept. Thank you.